some delay, yeah.
apologize for that.
No. After that, there will be again food and drink, so you can have a
Yeah,
drink.
why did I come here to begin with? Just for the food?
Exactly. You know, this is how you attract students. Yeah, food
Okay, so exactly.
is really.
Give them pizza and they will come.
Exactly, exactly. This is how
How
you
are
get.
you otherwise?
Well, otherwise fine, you know. Okay. Empty nesters now. Children are gone. They're in
many kids
LA.
do you have?
Two. The both are already working in LA. So I can travel more, give talks, have fun. Yeah,
Fun, no.
the group
I
is
don't
like
think you have fun.
you know,
Yeah, no,
I like science, so I just enjoy doing it. Yeah, and of course there is a lot of stress behind this because in addition to science fun, it's always chasing money, it's handling large group, it's fighting Drexel bureaucracy.
You can't have it all, you know.
Unfortunately, the price we pay for doing our jobs here. So that's a reality of life. But still, I would say, it's fun. As long as I enjoy doing science, I think I can handle everything else. Yeah.
It's always some new thing you learn.
Yeah.
It's always
Oh
new
yeah.
thing.
And it's it's really this family of material. It's so quickly growing and expanding. So it's a lot of fun. I want to take a picture of Moshe. Mm-hmm.
Ladies and gentlemen, friends and colleagues, good afternoon and welcome. Thank you for joining us today for the 2024 Marino Xanthos Memorial Lecture. My name is Moshe Kam, and I serve the students of NJIT as the Dean of the Newark College of Engineering, which organized this event. The lecture series was established by family and friends of the late Professor Marino Xanthos, who passed away in summer 2013. By that time, Xanthos has served as a professor of chemical engineering and director of the Polymer Engineering Center of the New Jersey Institute of Technology for 18 years, with earlier assignments in Martin Marietta, Resource International, and the Stevens Institute of Technology. He was widely known and respected contributor to polymer science, with interest in polymer blends, composites, and foams, polymer modification and reactive processing, plastics recycling and life cycle reassessment, and environmental considerations in polymer processing. This is the 9th time we are presenting the lecture, which is planned to be run by the Newark College of Engineering in perpetuity. We experienced growing interest and participation in the series over the years. I put on this slide some of the better known annual memorial lecture series in science and engineering. Among the ones that you see here is the Henry Morris Russell Lectureship before the American Astronomical Society that was established in 1946. The Richtmeier Memorial Award Lectureship by the American Association of Physics Teachers since 1941, the Fermilab Lecture Series at Fermilab, and the oldest one, which is the British Royal Institution Christmas Lecture in 1856. You can still hear one of those every Christmas Day, and here is a picture of the one that was given by Michael Faraday in 1856. Well, our lecture series is not yet that famous. but it's becoming a tradition. Just give us a few hundreds of years and see how far we have become. So far, we had the privilege of hosting Morton Den of the City College of New York, Thomas Russell from the University of Massachusetts Amherst and the Lawrence Berkeley National Laboratory, David Kaplan from Tufts University, Karen Woosley from Texas A&M University, Juan De Pablo from the University of Chicago, and Frank Bates from the University of Minnesota, Jan Vermand from ETH Zurich, and those of you who may remember last year, Professor Samuel Stubb from Northwestern University. All very well established, well known, and as it turns out, very interesting and enlightening speakers. Today's speaker and lecturer will be presented to you by Dr. Piero Armenante. Dr. Armenante is a distinguished professor of chemical engineering at NJIT, and he also served as director of the NJIT graduate program in pharmaceutical engineering. Actually, he still serves in this capacity. He is the chair of the Marino Xanthos Memorial Lecture Committee. Professor Armenante.
Okay, thank you, Dean Kam, and welcome to everybody. This is a yearly opportunity for me to welcome all of you to a very distinguished series of lectures. Actually, it's a combination of a little bit of work that we do on my part and the part of the committee that selects every single year the person that will be the speaker. And for me, of course, is a pleasure to have the honor, quite frankly, of introducing the speakers in general, and especially today's speaker, Dr. Yuri Gogosky. If there's a little bit of an issue that I always have at the beginning of these lectures, is to introduce the speaker, because if I start going through all the accomplishments that the speakers traditionally have, and especially for Professor Gogosky, then it will take a long, long time. So I'm forced to condense everything that I have to say in a few words. So Professor Gogosky is currently a distinguished university professor in Charles T. and Ruth M. Bach Endowed Chair at Drexel University. Now, before going into some of the other details I'm going to mention in a moment, let me give you a little bit of introduction to his distinguished career. So he got his PhD in physical chemistry from Kiev Polytechnic Institute back in 1986. And then he also obtained essentially the habilitation degree in materials engineering from also the National Academy of Science of the Ukraine. And he worked actually in Kiev, in Ukraine, after he finished. But then as soon as the Berlin Wall fell, he moved to the West, especially in this case, to Germany, and he was doing postdoc work at 3 different locations. Germany, of course, Japan, in fact, he speaks a little bit of Japanese, and Norwegian, and he used to speak Norwegian before. So after that, he decided to spend 1 more year at the Technical University in Karlsruhe, and then he migrated to the US. And first he went to University of Illinois, Chicago, where he spent a few years advancing through the regular academic career to associate professor. And then he was offered a position at Drexel University, where he is now. And there he really bloomed, quite frankly, because he has achieved a level of distinction which is difficult to compare to other more normal faculty members. So his research interest is in 2D carbides, nitrides, and carbonitrides, meaning the MAXenes, as they call it, spelled M and then xenes. And just to put things in perspective, okay, he has authored 2 books, he has edited 14, and he has co-author 800 papers, okay? Peer review papers. I think that's pretty difficult to achieve for most normal people. So he has a large number of patents, to be specific, 170 submitted, of which 60 already issued, and 30 of these have been licensed to industry, which means that his research is not only scientifically relevant in an academic environment, but also finds applications in industry. He has been cited 180,000 times. And his H-index is larger than 200. And more than 30 papers that he authored have been cited 1,000 times. One paper has 17,000 citations. I think that's quite difficult to achieve for most faculty members, I would say. I also have a list of about 2 pages worth of professional honors and awards, so I will not go through that, of course. I will only now briefly summarize what you probably have already in front of you, so I will not spend too much time on that. I already mentioned that he's a distinguished professor at Drexel in the Department of Materials Science and Engineering. He's the founding director of the A.J. Drexel Nanomaterial Institute, and he has been noted, and he's famous for the discovery of MAXenes and demonstrated the tuning of the structure and porosity of carbon-derived carbons and developed new processes for the synthesis, surface modification, and purification of nanotubes and nanodiamonds. So he was the first to publish a paper on the microbial observation of water inside carbon nanotubes and discover polygonal nanotubes. Again, I don't want to go necessarily through the list of other things that he has accomplished because, as I said, it will be quite long. And you have already the abstracts, but today's talk will be on the properties of MAXenes, this family of two-dimensional early transition metal carbides. And he will go over all the properties that these interesting compounds have, how can they find application for in a variety of topics in fields. I think I've talked enough. I think it's time now to hand the podium to Professor Gagotsi. Please welcome.
Thank you very much. Thank you. Can you hear me with this microphone? And I hope my pointer also works. I can see it on this screen, and I can see it at least like that on that screen. That's fine here. So unfortunately, there was no driver on the computer, so it will be just like a mouse pointer instead of a laser. First of all, you might have heard the song if you arrived early enough. It was written by Marcello Andrade, my former MS student, and he played the song as a surprise for me at a conference in France last summer when I came to teach in a summer school. And this is his advisor, Thierry Bruce. So if people write songs about something, that must be an exciting topic, right? And there is actually the second MAXenes song now. There is no video yet, but it's written by Ben Davis, my current postdoc and hard rock enthusiast. So if people write multiple songs about the topic, this must be something, again, very exciting here. And actually, my students in postdoc usually have many more talents than I do. I cannot write songs or play any musical instrument. I apparently can only do science. So what I'm going to do today is to talk to you about science. I will talk a little bit how discoveries are made. I will talk about materials and why materials are important. And of course, I will talk about MAXenes. For people who may not be familiar, those are carbides and nitrides of transition metals. Red atoms stand for a transition metal here. Black dots, carbon, nitrogen containing them. This is a very large family of materials, coming in different structures, coming in different colors, flavors, tastes, compositions. And I'm truly delighted to be here and give a talk in this very prestigious already lecture series. Sam Stapp, who was the previous speaker, is one of the best and best known scientists in this country. So I'm honored to be here. I'm really greatly indebted to the committee for selecting me. I'm not a polymer scientist. And while we work on MXene polymer composite materials, I don't think I can really tell you much about polymers, so I would stick to MXene themselves. I'm also glad to see in this audience my former postdoctoral researcher, Mark Xanthos, who is in faculty here. I'm delighted to meet Professor Moshe Kam, with whom we have been for many years colleagues at Drexel University. And of course, I always come visit universities to make new friends and eventually start new collaborations here. So again, look at these materials and think how and where you can use them in your research, in your area of activities here. But you have already heard about my travel around the world. But what I wanted to mention to you is that I started as a PhD student postdoc working on carbides and nitrides, bulk. I'm going to talk today about carbides, nitrides, but nano, building on my experience with carbon other nanomaterials, how we make them from three-dimensional conventional bulk ceramics to two-dimensional nanosheets, and explain what they can do. And you can go to our website and learn more about variety of research activities we have here. So I came from not very far away from Drexel University. For people who don't know, Drexel is located in Philadelphia. We are like a 20-minute walk from City Hall, which is behind the skyscrapers. My institute occupies an entire floor in this Boson Research Enterprise building. So this is like just 1 hour by train or hour and a half by car driving here. And I'm in the material science and engineering department. I know some of you are material scientists. Majority are probably not. But it doesn't matter because we live in the materials world. People define the history and progress of the humankind by materials used. From Stone Age to Bronze Age, Iron Age to the Silicon Age we're living now because we all use computers. I'm using this electronic pointer. Everyone has a smartphone nowadays here. Technology is really defined by materials available. But things change. We are moving, the world is moving. And I believe the future is different. It is in nanomaterials, assembled nanomaterials. And the reason is, main reason is here. Let me go back here. Because any great material you take has a certain set of properties. So pretty much you're bound by what is given, silica by silicon or by gold or by iron. When we take nanoparticles, we can assemble combinations of properties not available, not possible in any single materials. So what it means that we can move to new technologies, do things that fundamentally cannot be done with conventional materials or conventional even composite materials here. And materials I talk about today are exactly building blocks for this future technology. So we're going to talk about the building blocks for the future. And it doesn't mean that we will get rid of current materials. We are out of Stone Age, have been for a while. Patio in my house is still built of stone, and it's perfectly fine. We will continue using existing materials. But if you want to really fly to the Mars and live on Mars, or you want to make this planet cleaner and safer, we will need new materials things here. So basically, I went from three-dimensional carbides through carbon nanomaterials, and I'm going to skip 2 decades of my scientific life to this two-dimensional carbides and nitrides I'm going to talk about today here. But before I start talking about properties, and sorry, Piero, I won't be able to talk about all properties of MXenes unless you want to stay with me for a few more hours and maybe days, things here. But I wanted to tell you how we discovered MXenes first, because really serendipity is a part of many discoveries. We were working on lithium-ion battery anodes, trying to get lithium into layered titanium silicon carbide as anode material for lithium-ion batteries, which we failed to do. And when you push in something unknown that no one has done before, you don't know whether you're going to succeed. We failed. And really, failure is very often this path to success. When you do something that has never been done before, you may fail many times, but something you find as a result of failed experiments may lead to a discovery. So really, serendipity is something that is very important in many, many discoveries. Also other things, how we found water in nanotubes or these polygonal graphite polyhedral crystals on other things here. And this is not my statement. It comes from Barry Sharpless. Chemist in the room probably knows the name. This is a person who won 2 Nobel Prizes in chemistry. The last one like 2 years ago for click chemistry. So I guess he knows what he is talking about. And I think this is very important lessons for younger scientists in the room. Don't hesitate to do things that are crazy, unknown, has never been done before, or were told to be impossible here. Don't get disappointed when you fail to achieve what your advisor told you to do. Observe what you get. Try new things, and your discoveries will come. And this is how we discovered MXenes, etching max phases, trying to make room for lithium in this structure, something we have been doing for making carbon, selective etching process. I'll talk about it more. And well, this is actually updated. The paper, first paper we published is over 10,000 citations now, in fact, and it shows how when you do it once, it becomes popular and important. But this is another lesson for young scientists. We were very excited when we discovered MXenes, when we found first titanium-332 MXene. And we pretty quickly produced the first paper draft. And we submitted to a very top journal, and guess what happened? It got rejected without review. We submitted it to another journal. It again got rejected without review. This was, we discovered in 2010. We submitted in early 2011. This was just as Kostya Novoselov, Andrei Gaim got Nobel Prize for graphene. Everyone was excited about graphene. Dichalcogenides, silicene, germanium were discovered. And comment we got, well, you know, like so what is the big deal? Another 2-dimensional material. I contacted an editor of Advanced Materials at the time, Lorna Stimson, to explain to her why this is an important discovery, why this is not just one material. It's opened a new family of materials. And she promised to send the paper for review. And she did. And guess what happens afterwards? We got 3 lukewarm reviews explaining us how many other materials exist already, asking us to conduct properties studies on this and that, and the paper got rejected. Well, we asked for adjudication review, and 10 years later, when Advanced Material was publishing a special issue on MXene, because this paper became the most cited and most successful paper in the journal ever, we learned the name of this person. It was Professor Vincent Meunier. At that time, he was at RPI. Now he is at Penn State, who wrote this very short review that you can read here. So don't think whatever important you find, you believe important, you know it's important, but it won't necessarily be recognized right away. It may take time to convince people that it really matters, that it's significant. So again, don't get discouraged when your papers get rejected by journals. Don't get discouraged when your colleague not necessarily appreciate importance what you have done here. Believe in yourself, move forward here. And the paper got published, and the rest is the history. And Lorna came to me at one of the meetings with a bottle of champagne 3 years after publication, told, Yuri, let's celebrate that we published your work here. So, now let's go to science. What you see here is this very large family of two-dimensional materials available here. And what you will see is that they range from dielectric materials to semiconductors to semi-metals. MXene's that you can see here actually added purely metallic materials to this group. Materials with a high density of the state at the Fermi level, high concentration of carriers. What does it mean? We now have all building blocks to build devices, to build new materials. We have dielectric, semiconducting, semi-metallic, metallic materials. Keep in mind that graphene, which is being often praised for its conductivity, is a zero bandgap semiconductor. You have to either dope it and create defects to create carriers. In majority of MXenes, you have very good metallic conductivity, even with surface termination. And in graphene, you get graphene oxide, for example, or graphene, hydrogen terminated, and conductivity drops by 6-7 orders of magnitude. You basically kill it here. What does happen in MXene? Which cover variety of properties, including optical properties, optoelectronics, many others. So, how I look at the future of materials? I believe it's going to be materials which will assemble from solutions in a beaker from building blocks. Look at all these 2D materials like Lego stones or bricks that you build a wall, you build a house. What is important? You can combine them, nanometer thin flakes, particles, in any order, in any way you want. And when you take zero-dimensional, one-dimensional materials, you cannot build a complex structure with mechanical adhesion. And this is very, very important. Intimate contact between particles in two-dimensional materials really makes a difference. You can transfer electrons, you can achieve mechanical strengths, you can build multifunctional materials, and I will show you some examples later today. So really, we're not looking anymore for any wonder material, whether it's a graphene or nanotube or new metal or something else. We're talking about how to get properties that we need, that we can use artificial intelligence, machine learning, computational technique to predict what we need and think how we can assemble them from available to us building blocks here. Now, what are MXenes? There's layered materials, nanometer or thinner, built of couple of layers of transition metals connected between each other by either carbon or nitrogen. So we have a dozen of transition metal. We can have lanthanide substituting for one of them. Carbon, nitrogen, oxygen can substitute for, again, carbon, nitrogen, mixing oxycarbide, oxynitride. You can make carbon nitride. You can mix and match those elements, and transition metals will not stay non-terminated. They will pick whatever is in the environment, synthesis, or you can replace elements, and you can get halogens, you can get chalcogens, oxygen, hydroxyl groups, you can get phosphorus, antimony. We predicted that arsenic can also be there, just someone needs to go and make it. So do a simple math, number of permutations. Carbon, nitrogen, dozen of transition metals, a dozen of surface termination. You end up with at least 1,000 of new two-dimensional materials. But you can make carbon nitride, you can make solid solution X side, you can make solid solution M side. Metal stands for M, X carbon nitrogen, again, T surface termination. Infinite number of materials can be created. When we published the first material, this was titanium-32 in 2011 with oxygen OH terminations. There are more than 50 simple structures have been reported by now, more than 50 solid solutions, and I don't count the surface termination, which can be oxygen, OH, chlorine, fluorine, bromine, sulfur, and others here. So we get pretty much infinite number of materials that we're creating in the lab. We're trying to study their properties, and based on properties, develop applications here. And of course, for so many materials, I won't be able to discuss all the properties here. So how did we make them? We tried to use for lithium-ion battery anodes materials that were built of layers of silicon and separated by layers of carbides or nitrides. And the idea was to get lithium around silicon layers. And these materials are a part of large family of about 350 known at the moment, synthesized experimentally, so-known max phases. And as I mentioned, lithium didn't know about our DFT calculations and probably did not care about them and refused to go in the structure. So what we decided to do, to slightly etch one of the elements to make space for lithium to go in. As a result, these flakes were formed as a result of falling, basically breaking apart the max phase. And since these elements, materials were called max phases, after M is gone, M and X is left, so it became maxine. The suffix in was added simply similar to graphene, silicene, germanine to show two-dimensionality of these material things here. We publish extensively on how to make them. You can look at our paper. We teach twice a year an online week-long course on maxine synthesis. I won't go in detail. What I think is important for you now, that we have all these materials and we constantly improve the diversity of these materials here. So we can not only make these 4 structures I showed to you, but we can also make like atomic sandwiches. Materials where one element, for example, moly or chromium is on the surface, controlling chemical, electrochemical, catalytic properties. Another element, like titanium, is in the middle, controlling the transport properties. We can make materials with alternating atomic columns of metals, like in-plane ordered maxine. And we can etch away one of the least stable one, for example, in yttrium moly or yttrium tungsten carbide, leaving atomic trenches in the material, like a vacancy lines go in the surface. So I get the idea, hope the idea. We can really do atomistic engineering of these two-dimensional layers, playing with variety of elements, playing with a variety of structures. And we can mix and match different elements, making solid solution and even high entropy multi-element maxines. And actually, I took it from our science review from 21. These materials were marked to be discovered. Guess what? They have been discovered, they have been made in the lab, up to 7 different transition elements in high entropy maxines nowadays. So there is virtually no limit to what we can do. And of course, add to this surface terminations, which also are very, very important because they control really surface chemistry, surface properties of these materials in here. And of course, carbides and nitrides were just the beginning. People make now two-dimensional borides, silicides, and other materials here. And of course, navigating the sea of materials is impossible without computational science here. We did some work, this work with Professor Vivek Shenoy on machine learning. There are challenges. We need better data. We need really databases that would include material, all the properties of maxines, but it works, and there is more extensive work going on. This example not from our work, this example from very nice work from our collaborator from Linköping, Johanna Rosen and her colleagues, where they predicted which of layered compounds, not only max phases, but others can be etched, where a element can be removed, and they also made new type of a silicide to dimension on this. And there was a paper, this was published in Science a couple of months ago, I think earlier summer, and there was a paper in Science a week ago from Korea, from 17 groups, different groups. It's really a major undertaking when they predicted how by taking alkaline element out of layered oxide structure, replacing with protons, they can again take apart materials and make new oxide, two-dimensional oxides. So I think this is where we are going with the discovery of materials in here. Now, as we learn which layer structure we can etch, which not, we can develop methods for the synthesis. What is important? Let me also stress. Why can't we take this max phase structure, for example, or other compounds, and mechanically exfoliate, like graphene from graphite, or molybdenite from molybdenite, or boronitride? Because in those materials there are weak van der Waals bonds between the layers that you can break mechanically. In this case, we have strong chemical bonds with, say, silicon, titanium, aluminum, moly, or others, which cannot be broken mechanically easily here. So what we have to do, we have used chemistry to remove these elements. And what is interesting, it appears that we can actually remove monatomic layer of elements at the moment up to about 100 micrometer distance. Think it's a few angstrom layer, and you over 100 micrometer, what is the aspect ratio? Uniformly from large volume of material to make two-dimensional material from this layered ceramics. And there are by now many method synthesis. When we started to make them, we used hydrofluoric acid etching of titanium aluminum carbide. This is how first MXene was made here. And this method, let me actually remove John for now. This type of wet chemical etching was a used mix of different salt, acids, electrochemical, alkaline. We end up with a material having oxygen, hydroxyl groups, and maybe some halogen like fluorine on the surface. They are hydrophilic. They can be dispersed with water without any surfactant because they have high negative charge. Zeta potential usually between minus 30 and minus 80 millivolt. So they form stable colloidal solutions. But if we use halogen etching, gaseous, molten halogenide salts, or CVD synthesis, we end up with a material terminated by halogens, chlorine, bromine, iodine. They will be hydrophobic. They will have different properties. It's much easier to do with them chemistry on the surface, substituting chlorine with, for example, organic molecules. You can make hybrid organic inorganic materials. But the point is that we have many methods for synthesis, and the synthesis method to a large extent determines surface termination properties. What is also very important, we have infinite number of new materials. We can produce them by a variety of different methods. But to make a difference, we need to be able to make materials in quantity. And we take ceramic powder, basically, max phase, put it into etchant, whether it's liquid etchant or in a reactor and run gas by, or molten salt. It's really the size of the reactor that determines how much we make. So this is my former postdoc, John Wang, who just started 2 months ago at University of North Texas as a faculty member, holding 1 kilogram of titanium carbide MXene. It's a not a delaminated material, yet clay. And this is my former undergraduate student, Marley Downs. She just started again 2 months ago at University of Chicago as a PhD student with Dmitry Talapin, holding about 2 gallons of delaminated solution of single-layer niobium carbide flakes. So when you can make materials in a process that allows you to make quantities, you can think not only about sensors, small optical or electronic devices. You can consider large volume, large scale application, water filtration, energy storage conversion, and many others here. What is also important, wet chemical or molten salt etching methods that we developed like a decade ago or more are good in terms of we can produce volume of materials. But we also need to wash, we have toxic chemicals, water. But Dmitry Talapin published this paper in Science in March 2023. It was on the cover of Science magazine on gas phase synthesis of titanium-2 chlorine terminated MXene. just like less than a year later, the group in China, including one of my former PhD students, published a paper on fluidized bed synthesis of MXene from titanium chloride and methane. What is important? All white paint you see on the walls and the ceiling is titanium. Titanium was produced 3 million tons just in China alone in 2023 by so-known chloride method, taking ilmenite, iron titanate, treating with chlorine and carbon, and after that oxidizing titanium chloride with oxygen, producing titanium. Titanium tetrachloride is an intermediate product for synthesis of titanium with cost which is very minuscule. Now, you also may be familiar with carbon nanotubes, which are produced by chemical deposition, fluidized bed from methane, natural gas, by injecting catalyst. I don't know how many tons altogether in the world. I found, for example, Chinese company making 400 tons per year nowadays. But in every battery of every cell phone, every computer, you have every car battery, of course, there are carbon nanotubes as reinforcing and conducting additive here. So both are commodities nowadays here. So pretty much what we do, we work at the same temperature and synthesis of this MXenes. Methane, natural gas, is less expensive than oxygen. So what it practically means that we should be able to produce MXene in million tons if necessary. And then we can use it pretty much for every possible application. So it's really economy of scale. So we have virtually infinite number of new materials. We can make them by a variety of different methods, in a variety of different structures, chemical compositions, in highly scalable processes. But moreover, what is important, many of them are made of abundant elements. We had a Bronze Age, we had Iron Age, we had Silicon Age. There was no Gold Age or Diamond Age. And the reason is that whenever you have rare elements, they can be pretty, they can be useful, but they cannot make a huge impact that defining civilization. We need materials that can be made of elements that are abundant, that can be used everywhere. And if you look at elements we used to make MXene, titanium, just from titanium, it's a small subset of the structure you can create. VHA, aluminum, silicon. We have carbon, nitrogen in the structure, oxygen, fluorine, sulfur, chlorine, bromine, iodine on the surface. And other elements like vanadium, zirconium, niobium, moly are close enough. So we can make them of Earth's abundant elements. So it means that it's simply economy of scale. As long as we need material, we will be able to produce them in very large quantities at very low cost. And this is why one of the reasons I believe this material can make a difference. But isn't it great? Yes, it is. But if everything what these materials can do can be done by using clay, graphene oxide, or dichalcogenides, well-known, well-studied two-dimensional material, why bother, right? So the key thing is getting properties that other materials cannot give us here. And one I already mentioned to you. It's a high metallic electrical conductivity. For example, for people who don't know, if you take graphene oxide and reduce it to make reducing graphene oxide, which is widely used as building block to make conducting film, papers, coatings, you will get, with high temperature reduction, 2,000 to 4,000 Siemens per centimeter. With MXene, we can take these flakes, assemble them in MXene paper, like a film, spray on the surface, and we get 20,000 to 25,000 Siemens per centimeter. So about 10 times better conductivity, higher conductivity. But what is important? These flakes are hydrophilic. Again, comparing, they are like a hydrophilic like graphene oxide. They can be dispersed in water without any surfactant or additive. There is no binder to make a film. You just dry it, and you get a metallically conducting film on the surface, which cannot be done with other materials. Take metallic nanoparticles, you need a surfactant, you need to burn surfactant, and so on here. And Those flakes are single layer flakes of titanium 3C2 in this case, sitting on a silicon wafer. This is actually an optical micrograph. I've never seen single layer flakes of dichalcogenides or oxides of that size. And the reason is very simple. They will break from just a vibration in liquid. What does it mean? MXene is very strong. It's strong and stiff. Only ideal crystals of single layer graphene or boron nitride will be stronger. It's stronger than any other solution process to the material. So you get material metallically conducting, very strong, processable from pure water, the cheapest and safest solvent here. And they come, as you have seen, variety of colors, very diverse plasmonic properties, very strong interaction with electromagnetic radiations from X-rays to microwaves and radio waves. Plus, all these properties are highly tunable. Plus, biocompatible and non-toxic. At least I'm talking about titanium carbide, niobium carbide, tantalum carbide, number of materials. Of course, I cannot generalize in that particular case here. So that's very important. But the most important thing is here, they're tunable. Nanoscience is not about making things small. It's about controlling things at the nanoscale. And you can control during the synthesis by controlling number of layers, type of elements you use, by mixing and matching different elements, but surface terminations. You can also intercalate ions or graft organic molecules to change properties further. And of course, different materials will have different properties. But what is important? You can also change it in situ, because the density of state is sufficiently high to give metallic conductivity. For example, D elements of transition element give it to you here. But it's not as high as in gold. You inject charges into gold or copper, and properties not change by a dime. In MXene, for example, you replace oxygen with hydroxyl. Oxygen takes 2 elements from transition metal. Hydroxyl group takes 1 electron. And you can do it by applying about half a volt charge when you have protons between the layers. You protonate, deprotonate the surface. And work function changes, for example, from 6 to 2 electron volt. And you can tune, so you have a metal, the properties of which you can tune like semiconductor. All our electronic industry is based on semiconductors because we can modulate their properties. Now we can have metallic materials, two-dimensional, where you can modulate properties. So we can make electromagnetic interference shields that you can turn off and on, or infrared thermal management films that again can keep you warm or cold, and you can switch it with applying less than 1 volt voltage here. And this is very important. And of course, many properties are built in, and in many cases, they can compete with many other materials. And one of them, for example, their ability to absorb electromagnetic waves or reflect them. And this picture you might have seen before. It's a kind of a classical picture shown in textbooks everywhere as the first example of human-made nanotechnology. This is a Roman cup from the 4th century. The original is in British Museum. And it is red in transmission when you look through, and it's a green in reflection. And the reason is plasmonic gold nanoparticles inside glass. And actually, last year, Nobel Prize went for plasmonic nanoparticles. And the Russian scientist, who was one of 3 researchers, got it for actually what he showed, that controlling size of metal particles in glass, one can control the color because of plasmons. Now, titanium 2C is red in transmission, green in reflection, because it absorbs at 550 nanometer, just like gold. Moreover, we can apply small potential, and we can shift the absorption peak by about 100 nanometer in titanium 3C2 by 200 nanometer, making it also electrochromic. So this is just an example how we can basically control and modulate the properties to achieve what we needed here. So you see, and if you move to titanium 3C2, just add 1 layer of carbon element and 1 layer of titanium. The absorption peak will shift to 780 nanometers. So it will become actually now green in transmission green in transmission, and kind of a violet reddish in reflection here. So this is just one example here. So what we do with these materials? We get this material variety of properties. We typically process them simply from solution in water, but you can disperse them in polar organic solvent or modify the surface by organic molecules, and then you can disperse them, or chlorine terminated MXene and non-polar solvents as well. And making actually films is very easy. You can see if this video works. By Dr. Bladen, simply you spread colloidal solution of liquid crystalline concentrated flake, dry it. And this is my student, Gita Valoroso, is rolling a film away. This film is just 1 micrometer in thickness. Simply produced from solution, colloidal dispersion of flakes, and dried. What is important? It has strength of a high quality aluminum produced at room temperature. Conductivity, at that time it was paper from 2020, 15,000 Siemens per centimeter. Imagine, for example, batteries. When you replace 1050 micron metal film with 1 micrometer film, you cannot make a freestanding metal film foil in a micron easily here. And you can make it out of MXene and make it at room temperature from solution. Well, Mark was a pioneer in combining graphene with MXene. And you remember what I mentioned at the beginning. We have many, many two-dimensional building blocks. And they allow us to achieve combination of properties that can be made by a very simple way again. He did it by spray coating layer by layer and making this large sheet of material. You see in a cross-section it looks like similar to graphene paper, and studied electrochemical properties. We were looking for electrode materials here. This is a paper more recent, coming from Chinese Academy of Sciences and Ray Bachman from University of Texas, Dallas. They combined MXene with graphene oxide, similar what he did, reduced it with HI, and also added an organic molecule that bridge the layers, and dried it. Room temperature material. This mechanical strength is 1.8 gigapascal. This is twice the strength of steel. Now imagine, you make at room temperature from solution material that has twice the strength of steel. Not enough. This material is not only electronic conductor, it is an ionic conductor. This is what Mark did. It shows very nice capacitance. It shows redox reaction. Here, storing energy, cyclic voltammograms. So we get a material which is super strong, can be put onto any surface, anywhere, into any shape, three-dimensional others, and can conduct ions. What can we do with this? We can make a structural battery, or we can make an electrochemical actuator. Everyone talks about soft robotics, but soft robots are too soft to perform work, doing heavy lifting. Hard robots are heavy. You get a robotic snake that has 40 or 50 step motors and has a cable as thick as a snake behind moving. Imagine now you have just a snake skin which works as an electrochemical actuator when you apply less than 1 volt voltage, and it can basically move, change in the shape. Or imagine airplane or a drone that flies not just fly today, but like a bird, because you have wings which are strong, but can change their shape, electrochemical actuation things here. So those are new technologies I'm talking about, enabled by materials that simply didn't exist before, that have ionic electronic conductivity and strengths combined. Plus it can do electromagnetic interference shielding better than pure metal, many other things here. And this is, again, something that's truly important. And this is simply self-assembly. It's simple chemistry and processing from solution. Think here. So I think this will allow us to go into this futuristic technologies. And this is how I want everyone here to think about those materials here. What properties are you looking for? What you cannot achieve with existing materials? How can you take this new emerging building blocks and combines them into materials with properties that cannot be achieved here, especially if you talk about printable, wearable, other devices here. And my students started a company recently. They're scaling up technology, Maxine Inc., for industrial applications. Naturally, when you have so many materials with properties, with scalable technologies, applications are emerging. And because the material is so diverse, pure materials or combination with other, they cover from energy storage and harvesting to communication, to environment technology, water desalination, gas separation, purification, to optoelectronics, sensing, biomedicine, many other fields here. I'm going to give just a few examples to finish on time and leave time for questions here. In my group for many years, we have been working on materials for electrochemical energy storage. Actually, the most cited paper I have that was mentioned, Professor Eminante, is not on Maxine's. This is on materials for electrochemical capacitors, things here. And if we're talking about wearable, flexible, printable energy storage devices, we cannot use existing technology. We have to use nanomaterials. This is a review article we published with a couple of colleagues in Science a few years ago here. So let us look at Maxine's. Why and what can those materials do? And this is typically first question I ask my students when they consider and come to me and tell, Yuri, let's try Maxine 00. I tell Azam here, why? What can they do that other materials can't? And what Maxines can offer? They have high electronic conductivity. Even if you do surface redox, it stays. They have on the surface moly, vanadium, niobium, titanium. Actually, many of the same elements that are used in current battery materials. Transition metals, we have different degrees of oxidation and can change their oxidation state. And you can change the oxidation state of elements on the surface without disrupting the structure. There are no phase transformation happening. They also have channels for transport of ions between the layers. And all active elements are on the surface, so there is no solid state diffusion. Now, what do we want from new energy storage materials? If you look at this plot, which is called Aragoni plot, it's a plot power versus energy. You will see that there are two types of devices, roughly. Electrochemical capacitors that store energy in a double layer. It's a physical storage, very fast. Adsorption, electrosorption, desorption of ions. They're widely used, but the amount of energy stored is limited. It's a double logarithmic plot, keep in mind. And there are batteries. They store more energy, but there are redox reaction, phase transformation, solid state diffusion, so they store slower. What everyone wants, devices that will store a lot of energy and can be charged, discharged quickly, that you plug your car into a charging device in a charging station, and just like with gasoline, 2 minutes later, you can drive further. Or you can plug your cell phone into outlet, unplug it, and it's fully charged here. So what do we need for this? We cannot go with double layer storage, right? Because physical storage simply cannot give you enough energy. You cannot go with solid state battery typically because solid state diffusion fundamentally is slow. You need materials that are capable of doing redox reactions that you can store more energy. You need materials when there is no solid state diffusion, so it means must be surface storage process. And what people forget often, it's a conductivity. This is well hidden secret in the battery community. What does it mean fast charging? It's very easy and simple. It's simply running a high current through your battery. What happens if you run a high current through a poor conductor? Joule heating. It means that car batteries have this expensive, complicated cooling systems, which makes it bulkier, heavier. It also means that a lot of energy that we produce goes into waste, hits the environment when you charge and discharge. Titanium-32 Maxine has conductivity two orders of magnitude, higher compared to porous carbons that use supercapacitors, the fastest energy storage devices. So if you combine all these properties, this may be a way to make this fast charging very efficient energy storage. But there are many challenges. You need to learn how to deal with ions and pores, other things here. But you can do similar energy harvesting because you can do it much faster process here. Let me give just one example, when I think it's kind of simply striking, not the most popular one. You might have heard about transpiration-driven electrokinetic power generators, or probably not. Because it used to be for a long time a scientific curiosity, demonstrated about 10 years ago. It's simply a fancy word for energy derived by flow and evaporation of liquid when ions move with evaporating liquid. It was shown on carbon, but the power generated was so small that it was absolutely impractical. Using hydrophilic and highly conducting MXene, when you get much lower resistive losses, enable to go 2-3 orders of magnitude in power density with this material thing here, simply replacing carbon with MXene here. It shows how big the improvement. We're not talking about 10-20% factor of 2. We're talking about orders of magnitude, just like I showed with mechanical strengths here. And of course, when you have two-dimensional material with slits which have different dimensions, different surface charges on the surface, so on, you can talk about separation, desalination, gas separation, ion elimination here. There is very fast rise of use of MXene in biomedical research. Again, started virtually in 2018 after minor noise, but it is on a very, very quick rise. Those data come from November 2023, as you see things here. Going from photothermal therapy, using this light absorption and heating by infrared or near-infrared light to treat cancer, to tissue engineering, particularly, for example, conducting cardiac tissue for cardiac surgery, replacement here, to sensing, wound healing, intraocular lenses, which again use optical properties of MXene and electrochemical actuation and many others here. Just a simple example. We work with Professor Flavia Vitale across the street from us, University of Pennsylvania, on making epidermal and implantable electrode with MXenes. Epidermal electronic sensing is a very popular topic now because probably 10 years down the road, we won't go to doctor office for medical diagnostic. We'll have sensors wearable on skin that will pretty much do all the diagnostic, send information through our cell phone or whatever, probably embedded communication devices to supercomputer, which will give you diagnosis better than any doctor here. We need for this electrodes, which are cheap, compatible with skin, which can give good results. Today, people primarily use gold everywhere. If you look at all epidermal electronics, it's all gold. And you realize it cannot be used by everyone and thrown away after use if it stays this way. It will never become common. It's like, for example, like a thermoelectric made of tellurides. Will always become exotic because it's too expensive. Titanium carbide MXene gives you much higher sensitivity. You see this type of spikes compared to commercial gold sensors and lab-made gold sensors. Not because it's more conducting than gold. It has simply lower impedance with skin. As a result, you get higher beta sensitivity. And it can be made of titanium carbide, which will be much cheaper here. Of course, you can embed it in textiles somewhere else here. I see I have a pocket square, which was screen printed with 3 different MXenes by my students more than 2 years ago. You can see word MXene typed here. It's perfectly fine after several years. It stays there. It's still conducting. It has different infrared signature and so on. And you can wash these textiles, and they stay at textile electronics here. MXenes have different infrared properties. And what is interesting, some of these MXenes emit very well in infrared range. You can use them as, for example, special heaters. But some of them are as reflective as polished metal. So what it happens? If you print, for example, like a Drexel logo, like a dragon I'm wearing here, on a glass and put on a hot plate at 80 degrees C, if it's made of carbon, it will accept the same temperature as a hot plate. It will stay cold if you make it of MXene. There are 3 different MXene films here. It's 200 nanometer film on a 120 degree hot plate. 200 nanometer film drops the temperature by 80 degree in this case. Imagine painting every wall of the building with a material which is reflective in air and has, unlike metals, thermal conductivity well below 1 watt-meter Kelvin. About more than 1/3 of all energy we produce in the world is used by buildings. About 1/3 of this goes for heating and air conditioning. Imagine how big impact can be on heating the environment if we can have a paint that can really insulate and protect building, minimizing the amount of energy we need to use for cooling and heating. Or imagine a silk dress like I showed to you that is coated with MXene, and it keeps you exactly as warm as a thick insulation or as a space heat shield that are used here. So you can have a silk dress, and it will be as warm as a fur coat because it's not losing, you're not losing energy through radiation, and at the same time, it has very low thermal conductivity. And of course, it provides infrared stealth. This is a t-shirt that my student washed simply in MXene solution, and you see now it looks cool, so there is no temperature losses from the body happening here. So I think those just gives you glimpse of application, very, very different. There's another application where for waveguides for satellites, replace metal with a printed polymer. You dip it into MXene film, use milligrams of materials, and you get a waveguide which is 10 times lighter. And imagine, as 100 grams a waveguide, standard one, it can be larger, the kilogram. And cost of lifting to space is $10,000 to $20,000 per kilogram for liftoffs. Here, you can make it 10 times larger and actually 10 times cheaper with laboratory-produced MXene compared to making it out of metal things here. Many other applications. We work with Korean colleagues to replace transparent electron transport layer in LEDs. ITO, which is used today in indium tin oxide, transparent conductor with MXenes. Initially, they used it to make LEDs flexible because ITO cracks when you use it on the surface. But what they found, because we can tune the work function, remember I mentioned depending on surface termination between 2 and 6 electron volt, they got 10 times increase this logarithmic scale in brightness, luminance. And now we can make also them stretchable up to 40% roughly without losing performance. So I think this is how you need to think about new materials, where you cannot improve something by a few percent, but talk about order of magnitude improvement. Talking about things that are simply impossible with other materials. You cannot make a stretchable organic light emitting diode by using ITO things here. And Hussam Al-Sharif suggested the term maxitronics, building basically a roadmap to electronic devices with MXenes here. And of course, there are two-dimensional materials with interesting quantum properties. So again, quantum materials realm, this is again another opportunity for the field here. Naturally, there are many applications emerging. But we're at the beginning of the road. Look at all these papers on MXene. We discovered them in 2010, published first paper in 2011. There was really at a noise level number of publications until they started to show properties exceeding all other reported in the literature for other materials, and you see it started growing up. For example, sensing. There was almost nothing 5 years ago. Now it's a large segment of all the publications. And if you look at this, There are all kinds of sensors, from electrochemical to humidity, biosensors, pressure sensor, gas sensors, optical sensors, and so on with every other field. So it's emerging. There are companies that manufacture vaccines. Also, if you want to read about this really fascinating family of materials, this March 25th issue of CNN with a cover story running about a vaccine and centerfold is really very nice, introductory, easy reading here. Of course, there are people all over the world working in the materials. Asia is leading, but there are already thousands of patents, so the field is picking up. Still, we are in the very beginning of the road. We have more questions than answers. We need to understand how to make many, many other vaccines that we have not been made in the lab yet. Controlling surface, defects, interfaces and junctions here, mapping all these possible variation of properties, predicting materials with extreme properties. Rational design of hybrid materials, how to combine. Now we have an infinite number of 2D vaccines. How do you combine them with other materials, which is another infinity. It's infinity multiplied by infinity. Things here. This is exciting, but it's exactly what requires guidance from computation, from artificial intelligence. We cannot do it experimentally in the lab. And even many theoretical predictions have not been confirmed yet. For example, chemical tunable superconductivity has been demonstrated, but chemical tunable ferromagnetism, not. Or topological insulators that have been predicted to be multiple are to be made here. And of course, we don't know yet what will be the killer application. There are multiple, I show you today, possible today. And I think this is where the excitement is. There is plenty of room for discovery for everyone. You can go back to the lab, make new material, start using this material, explore their properties in your applications, whatever you're looking for. There is already a journal, Graphene and 2D Materials, edited by one of my former postdocs, Babaka Nasuri, which pretty much represent graphene and vaccine community, published by Springer here. And those are my kind of last slides. It's a message again to PhD students, younger researchers working here. So again, just believe in yourself. There are ways to change the world by developing new materials here. Be critical to everything what has been done before. Doesn't matter whether you read a paper of a Nobel laureate or another famous scientist. Don't hesitate to challenge the existing knowledge here. And be agile. You find something new, you find something interesting. Don't hesitate to switch your research direction. Make a U-turn, jump a new opportunity. Don't walk by telling, oh, you know, that's not what my advisor asked me to do. I got something new and different, but I was supposed to do something else here, so I will put it aside and continue with my PhD research. You get something new, different, go after it. Try to understand it. This may be your big discoveries here. So again, follow your dream, believe in yourself, never, never give up, and your discoveries are waiting to happen here. And this is my very last slide. Of course, everything I do is not done by myself. I have a wonderful, very diverse group of students, postdocs, from at least a dozen of different countries usually. This picture was taken just a week ago, actually exactly a week ago after our group meeting on Wednesday last week. And I was surprised to count that we have more women than men in the group. And I didn't know how many, because we never hire someone because a person is different, minority. We just go after good scientists, people who share our values, who are excited about our ideas. And these people working as a team make all the difference. Those are the ones who make discoveries. But even with a very large and diverse group, we still can do everything. We don't know everything. I don't know everything. My students know more than me. But still, we collaborate with many people, and you can see again from around the world, truly around the world. There are great scientists everywhere. Whenever we work on implantable electrodes, biosensors, ophthalmological application of vaccines, or antennas and waveguides for space application, we work with people who are specialists in the field. So again, don't hesitate to get outside your comfort zone. Talk to people about topics you're not an expert in. Learn from them, explain to them how you can collaborate, because the most exciting things happen at the interfaces between different disciplines. This is where least understanding exists. This is where opportunity for breakthroughs exist. So again, talk to people who work in different fields. Go to seminars in different fields. Learn and think how you can participate, how you can make a difference with your research here. And with this, I want to thank once again the committee for inviting me. It's a great opportunity to give a seminar at NJIT, and I hope that you have a better understanding of vaccines. Read this CNN issue from March 25th this year if you need an introduction. And of course, if you go to our website, you will find plenty of resources about those materials and much more. And you will find also contact info for my students and postdocs. And as I mentioned to you, they know more than me. They're great contacts if you have questions about vaccines here. Thank you very much.
Thank you very much. What a great presentation. This was really
It's my pleasure.
Thank you very much. So, yes, take a picture, please. Thank you. Okay,
Yeah.
I think we can open the floor for questions. I'm sure there are plenty of people asking, so I'll limit myself to, the number of questions we can ask. Please. Sir, yeah.
Hi, my name is Xanthos. I'm the member.
Speak loud, please.
Okay. Very interesting and impressive work. By the way, I have a very close friend, Hao Chen, is in your department.
Oh,
we
yeah.
are
graduate student at Northwestern, and we went to the same lab at MIT. So back to my question. So what's the boundary, let's say, how many layers and the feature size in terms of surface area that affect the property of the vaccine? The second part of the question is, I saw the large-scale production. Is there any concern about the degradation, let's say environmental pollution, is this kind of a concern?
Look, I did not talk about millions of different things today. So about the boundary. So first thing here, we can make within this single flake from 2 layers to 5 layers of transition metal. If you take 5 layers of transition metal, 4 layers of carbon nitrogen, surface termination, you have 11 atomic layers. This is probably by far the thickest 2D material, really a giant of 2D world. It's still 1.3 nanometer thin. And flakes can be, currently we can make scalably up to 20 single delaminated, 20 microns, non-delaminated, 100 microns. And coupling between the layers actually much weaker compared to, say, graphene, because in graphene, you establish van der Waals bonds, and you go to graphite structure slowly. In vaccine, for example, the Raman peak will not shift whether you have 1, 2, or 3 layers. So there is less coupling between the layers. So within 1 layer, probably about 5, 6 transition element layers, it becomes energy-wise very close to bulk material. So there will be no properties differences. But we don't know where the limit is because no one made more than this 1.3 nanometer flakes at the moment here. Now, about others. Carbides, nitrides can degrade. They can transform to oxide, hydroxide. It may be good at the end of the environment, titanium carbide vaccine, and ends up as titanium dioxide and carbon oxides, so there is nothing toxic. But in many applications, we want them work for a long time. And I showed you this piece of silk imprinted. It has been a couple of years old. We know that we can wash it at 80 degrees. So many of them are not easy to degrade. The paper airplane I showed you somewhere, it actually was made 10 years ago. You probably know it, coming from PNAS paper hour, right? Yeah. And it is still in my office. It's still conducting 10 years afterwards here. However, you can oxidize, you can degrade them. Depends on the metal, depends on defects, strongly, stoichiometry and defects. And we need to control all those properties. we need to worry about the environmental fate of materials. But this study largely only recently started because when there were no application, no large-scale production, no one really bothered to work about it here. It's exactly the time to go much more detail, and not only for titanium carbide-based MXene, but for many other compounds.
Okay, thanks. By the way, is there any correlation between the number of the layers and their function?
Yes. Well, again, you know, like I showed you titanium 2C, titanium 3C2 have very different absorption peaks. You see shifted spectrum strongly, very different colors you can see here. But then if you get monolayer, double layer, we kind of are trying to study twisting also, doing some twistronic actually with Kostya Novoselov, and see if there are also any unusual properties depending on relative, basically, angle between the layers here. Again, this work just started very recently on this.
Okay, thank you.
Okay, any other questions?
Yeah, thank you. Thank you for the great talk. And I have a couple of questions. First one is you say the conductivity, and I want to look into the conductivity in two kinds. One is the electronic conductivity, and the other one is the ionic conductivity. And first, in terms of the electronic conductivity, I say it's kind of 2D plane. So in plane electronic conductivity and then the vertical directions electronic conductivity could be different. I want to see your opinion on if you have any data on that one. That's the first question. Second question is, in terms of ionic conductivity, you said a bunch of the variety of the applications. I'm thinking some kind of electrochemical systems, such as battery or fuel cell, or any electrochemical systems. In the cases, can you still use that MXene in the layer of the membrane or ionic membrane layer, ionic conductive applications? That's the question. Thank you.
Yeah. Well, basically, MXene's very similar still to many other 2D materials. Everything what we have learned for graphene and related materials, to a large extent applicable. Of course, there is difference in conductivity, both electronic and thermal and ionic, in plane and out of plane. But conductivity values are measured to you as typically as a 4-probe conductivity or van der Poel measured on a film. So it's in plane, but includes many, many, many different flakes for many, many stacks. What does it mean? There's very good, actually, tunneling between the layers. And we don't fully understand the mechanism. Moreover, let me tell you, you can take a MXene film with 2 monolayers of water between the layers and measure temperature dependence of conductivity. It will still be metallic. You can freeze it and get a material which will still, after hysteresis, as it freezes here, again become metallic after expansion things here. And how electron transport happens between the layers, so there is in-flake, within a flake transport, and interflake transport. It's still at fundamental level not understood. But yes, there are differences, but still it's a much better conductivity electronic between the layers compared to other materials. There are differences not such large. And the second question was about ionic transport. It's the same as other materials things here. So smaller flakes will allow your ions to move faster. Larger flakes will be an obstacle to ions transport. Vertical orientation, random orientation, in-plane ordering will all do things here. So they're controllable, but here there is no fundamental novelty or differences compared to other materials as we talk about molybdisulfide, two-dimensional oxides, clays, or graphene. For ions, there are just obstacles to move around. And of course, you can control selectivity or permeability will be controlled by spacing between the layers, surface charges, and so on. Different thing is here. You can apply a potential, and you have an extra, therefore, way to control it compared to graphene oxide membranes or, for example, clay membranes.
Okay, we are kind of over time now, so one more question.
Students, postdocs, don't be shy. You are the future of science. You are the one who will be making discoveries and creating the next generation of materials. Was it so confusing?
Let's not embarrass them. Let me ask the question then. Okay. All right, so probably a number of people here are chemical engineers. So what are the challenges, we discussed this already, but what are the challenges that you can imagine that people will encounter when they scale up facilities to manufacture this, this interesting compound?
Well, Maxins just recently start moving from lab scale or batch scale small production in industry for research purposes to larger scale manufacturing. And we're facing the same challenges and every process engineer, I think, faces things here. For example, if you want to go to large volume fluidized bed synthesis here, how you design the process? It's the temperature, it's flow, it's research engineering. When we go to synthesis, wet chemical synthesis, we use acids. We use a lot of water to wash acid and or salt. After that, we do the elimination, and we again use intercalate lithium ions or tertiary amines, and again use a lot of water. How do you minimize the use of water? How do you capture small particles and don't let them go with the flow? We use in the lab centrifuging, which is a very expensive and inefficient method. You definitely want to move to filtration, dialysis, other techniques in industry. And this is enormous room for chemical engineer, and it's really timely. 5 years ago, no one really cared that much about large volume production. Nowadays, people do care, but there is no large volume production. And developing a low-cost, efficient, safe process for synthesis and elimination of Maxine will be critically important. And I think this is an enormous opportunity for chemical engineers. You can use knowledge existing with work with, for example, clay and elimination, layered double hydroxide, graphene oxide from the more recent history, or other materials. But how do you apply it to Maxine? What is applicable? What is different here? So we are very much interested in this, and I think this is a very, very timely topic to explore.
Well, thanks again very much. Before just concluding this session, let me mention that Professor Rogoski will be here for about an hour, well, no, less than that. If you have any questions, if you'd like to talk to him, interact with him, feel free. The last remark is that keep in mind that Professor Rogoski could have been now giving a talk and attending a conference in Hawaii, and he chose instead to be at NJIT. I'm not sure how many of you will do the same thing. Okay?
Well, I'm sure my postdoctoral research is enjoying Honolulu, and I'm delighted to be here and make new friends and have an opportunity to talk with all of you. So again, thank
you
for
again very
inviting
much.
me here.
Thank you. Okay, we have a little something for you, so please join me. Okay, sorry, there's something here. Well, it's very honored to have you here. I would like to give a little memento of what we have for you.
Thank you very much.
Thank you.
Thank you very much.
Thank you again. If you have somebody
Thanks
wants to
again.
take a picture, please.
Terrific.
Thank you again.
Very good. Thanks. Beautiful plaque.
Thank you again.
So we can actually send this to
Yes,
you,
exactly
because
what
we
I
know
wanted
your
to ask.
preference.
Let me give you something else. A package that I got.
So it was nice meeting you. I have a question.
It's my pleasure.
So it looks okay. So basically, you have these stoichiometric ratios. What if you try dope like the M site, right?
Yeah.
What if you have multiple species on the M site?
Yeah.
Can you tune
This
that to
is
get? Yeah.
yes. This is
Yeah.
what I call like high entropy Maxines that people
Ah,
make. There are
okay.
multiple species up to
Yeah.
like 7 elements
Yeah,
on the
yes.
M site.
Yeah.
You can unwire me.
Yeah.
Thank you.
Thank you very much.